Welcome to the deep dive. Today, we're diving into a paper
Okay.
that grapples with a really common problem. How do we solve those Bayesian inverse problems when, our forward model
Right.
isn't perfect? The paper's title is a bit of a mouthful. Inexact Generalized Golub-Kahan Methods for Large-Scale Bayesian Inverse Problems.
Yeah, it is. But it really captures the core challenge, right? Because in so many real-world applications, we just don't have that perfect knowledge of the system we're trying to model.
Exactly. So we're going deep into how the authors tackle that inexactness, especially when we're dealing with massive data sets and complex calculations.
And I do a really clever job of blending some classic techniques with some new adaptations to create a method that's both powerful but also practical.
I like that. Powerful but practical. So let's unpack this a bit. Imagine we have some data, and we're trying to figure out what caused it, the underlying parameters that produce that data.
Right.
That's our inverse problem.
Yeah. And in a Bayesian setting, we're not just looking for like a single answer. We want to quantify the uncertainty, incorporate any prior knowledge we have, and ultimately get a probability distribution over those possible parameters.
The authors talk about using the maximum a posteriori, or MAP, estimate to find a solution. This leads them to a generalized Tikhonov problem.
Right. Exactly. So the MAP estimate gives us those parameters that are most likely given the data and our prior beliefs. And that Tikhonov formulation is a way to regularize the problem, to kind of prevent those small errors in the data from blowing up and giving us crazy inaccurate solutions.
Okay, so far so good. We've got our Bayesian inverse problem. We're going for the MAP estimate. And we're using that Tikhonov regularization to keep things stable. But where does this whole inexactness thing come in?
Well, ideally we'd have a perfect mathematical model of the process that generated our data, but realistically our models are always approximations.
It's like using a map to navigate a city. It gives you a good overall picture, but there might be road closures, detours, construction things that map just doesn't show.
Exactly. And in a lot of applications, those discrepancies between the model and reality can really impact our ability to solve that inverse problem accurately.
So the authors are saying, hey, let's be realistic. Our models aren't perfect. And then they develop a method that can actually handle those imperfections, especially when we're dealing with these large-scale problems where just brute force calculations are out of the question.
Right. And they introduce this concept of error matrices to represent that inexactness without making the problem computationally intractable. And then they combine that with these clever adaptations of existing methods, like Golub-Kahan bidiagonalization.
I have to admit, whenever I hear Golub-Kahan bidiagonalization, my brain starts to go a little fuzzy. Can we maybe break that down a bit? What does that actually mean?
Of course. Imagine you have this massive matrix representing your system. Direct computations with such a large matrix can be incredibly time-consuming.
Yeah. It's like trying to find a needle in a haystack the size of a football field.
Exactly. So Golub-Kahan bidiagonalization is a technique that helps us break down that massive matrix into smaller, more manageable pieces.
Okay, that makes sense. So it's a way to reduce the computational burden, make the problem more tractable. But how does that tie into the Bayesian framework and that whole inexactness issue?
That's where it gets really clever. They start with the standard Golub-Kahan method, which is kind of a workhorse for solving least squares problems. Then they modify it to handle the fact that our matrix vector products with the forward model A and its transpose might not be perfectly known.
I see. So they denote these inexact products using A and NA, where eq and fleck represent those error matrices at each iteration. It's like acknowledging that our calculations are always going to have this little bit of fuzziness to them.
Exactly. And they don't stop there. They also incorporate a technique called generalized Golub-Kahan bidiagonalization, which is specifically designed to handle problems that involve covariance matrices.
Ah, yes. Covariance matrices. Remember how we were talking about quantifying uncertainty in a Bayesian setting? Covariance matrices are key to representing that uncertainty. They tell us how much different parameters are likely to vary together.
Exactly. So the authors combine the best of both worlds, a method for handling inexactness and a method for working with covariance matrices. That's how they create their star player algorithm, the Inexact Generalized Golub-Kahan Method, or igenGK for short.
igenGK, it sounds like a superhero of algorithms.
Yeah.
So this method generates a lower dimensional subspace where we can then solve our problem more efficiently. But how do we actually find the solution within that subspace, and how do they deal with choosing that regularization parameter?
Those are great questions, and the authors introduce some really clever techniques to address them. A method called igenLSQR to solve the problem in that reduced subspace, and a hybrid approach to handle that regularization parameter.
This is where it gets really interesting. Let's dive into the details of how those techniques work.
Sounds good to me. We're about to see how they combine that mathematical rigor with practical considerations to create a method that's both elegant and effective.
Let's start with the change of variables they introduce right at the beginning in section 2 of the paper. They want to avoid having to calculate the inverse of those potentially enormous covariance matrices, especially when dealing with complex kernels like the Matern family.
Absolutely. They introduce a new variable, x, which is a transformation of the original parameter, s, using the inverse of the covariance matrix, q. This allows them to reformulate the problem as a least squares problem without losing the ability to use those sophisticated covariance kernels.
That's a neat trick. It's like finding a shortcut through a maze. They're saying, hey, we can work with a simpler problem without losing any of the important information about the relationships between the parameters.
Precisely. And by transforming it into a least squares formulation, they can tap into a whole bunch of well-established methods for solving these types of problems efficiently.
Looking at equation 2.1, which represents that posterior distribution, they're using a Gaussian prior and a Gaussian likelihood, which leads to a Gaussian posterior. This seems like a pretty common assumption in Bayesian inverse problems, right?
It is. The Gaussian distribution has some nice properties that make it, well, mathematically convenient to work with. And in a lot of cases, it provides a reasonable approximation of the true underlying distributions.
They also point out that maximizing the posterior is equivalent to minimizing the negative log of the posterior. This leads them to the minimization problem in equation 2.2, which looks a lot like a classic Tikhonov regularization problem.
Right. The first term in equation 2.2, that represents the data fidelity term, how well the parameters fit the observed data. The second term is that regularization term, which penalizes solutions that are too rough or too complex.
And lambda is that regularization parameter that controls the trade-off between fitting the data and keeping the solution smooth.
Exactly. Choosing the right value for lambda is critical. And the authors explore different methods for doing that later in the paper. But for now, let's focus on how they handle the inexactness in the forward model.
They introduce their notation for those inexact matrix vector products in section 3. They use error and error to represent those inexact versions of the forward matrix, A and its transpose. And they use ik and phytkar to denote the error matrices at each iteration, AA.
This is where they start laying the groundwork for those inexact methods. They're acknowledging that in real-world applications, our calculations involving the forward model are always going to be a little bit off.
It's like acknowledging that our measuring tools always have a little bit of error, right? We can never measure things perfectly, so we need methods that can account for those imperfections.
Exactly. And instead of trying to eliminate those errors completely, which is often impossible, they develop methods that can work with those errors and still produce reliable solutions.
Okay, so we've got our Bayesian inverse problem, our Tikhonov regularization framework, and our notation for handling inexactness. Now, let's dive into the heart of their method, the Golub-Kahan bidiagonalization and its inexact and generalized variance.
Sounds good to me. It's time to unravel those algorithmic layers and see how they bring it all together.
They start with the standard Golub-Kahan bidiagonalization in section 4.1. They even provide a nice algorithm outlining those iterative steps involved.
It's like a recipe for breaking down that massive matrix into smaller, more digestible bites.
They generate these two sets of orthonormal vectors, UK and VK, and a bidiagonal matrix, BOK.
Right.
What's the significance of those vectors in that matrix?
Those vectors, they span what are called Krylov subspaces, which are essentially special vector spaces that are generated by repeatedly applying a matrix to a starting vector.
Okay, that sounds a bit abstract. Can we make that a little more concrete? Imagine we have a vector, B, and we want to solve the linear system ACL X, B, B.
Right. The Krylov subspace associated with A and B is the space spanned by B, A, B, A, A, B, and so on. It's like taking that initial vector B and repeatedly hitting it with the matrix A to generate new vectors.
So the Golub-Kahan method generates these Krylov subspaces and uses them to, like, iteratively find a solution to that least squares problem.
Exactly. And that bidiagonal matrix, BEEP, captures the essential information about the matrix A within those subspaces. It's like compressing the complexity of A into a more compact form.
Okay, I think I'm starting to get the gist of it. We've got our Krylov subspaces, our bidiagonal matrix, and now we can solve the problem within those subspaces using a method called LSQR.
Right. LSQR is specifically designed to exploit that structure created by the Golub-Kahan bidiagonalization. It's like a specialized tool for navigating those Krylov subspaces efficiently.
This all makes sense in the ideal case, where we have perfect knowledge of the forward model. But now let's bring in the inexactness. How do they adapt the Golub-Kahan method to handle that?
That's where the inexact Golub-Kahan, or iGK, decomposition comes in. They describe it in section 4.2, building upon that foundation of the standard Golub-Kahan method.
So instead of generating the matrix breed, they generate two matrices, MK and LK, which capture that inexactness in the matrix vector products.
It's like acknowledging that our map of the system is slightly distorted, so we need to adjust our navigation accordingly.
And they provide a modified algorithm that incorporates those error matrices EK, KFK into the calculations.
The key idea is to carefully adapt those iterative steps to account for the errors in the matrix vector products, making sure that the generated vectors still span a meaningful subspace.
Okay, so we've seen how they handle inexactness. But what about the generalized part? Where does that fit into the picture?
That's where the generalized Golub-Kahan, or igenGK, bidiagonalization comes in. They present it in section 4.3, extending the standard Golub-Kahan method to handle problems that involve covariance matrices.
Remember how we talked about the importance of those covariance matrices for representing uncertainty in a Bayesian setting?
Exactly. The igenGK method is specifically designed to work with those covariance matrices. It generates different sets of orthonormal vectors that span Krylov subspaces related to the matrices AQ and AR1, where Q is that covariance matrix and R is the noise covariance matrix.
So it's like taking the standard Golub-Kahan method and giving it a Bayesian upgrade.
Precisely. It allows us to incorporate those crucial covariance matrices into the bidiagonalization process, ensuring that the generated subspaces capture the essential information about the uncertainty in the problem.
And now for the grand finale. They combine the best of both worlds, the inexactness handling of iGK and the covariance awareness of igenGK to create their super method, the Inexact Generalized Golub-Kahan Method, or igenGK.
They describe igenGK in section 4.4, bringing together all the pieces we've been discussing. They combine the approaches of iGK and igenGK, adapting those iterative steps to account for errors in the matrix vector products, while also respecting the structure imposed by that covariance matrix.
And they provide a detailed algorithm outlining the steps involved in this powerful new method.
It's like they've taken the best tools from two different toolboxes and combined them to create this super tool that can handle a much wider range of challenges.
I'm really impressed with how they've systematically built up to this point, starting with that classic Golub-Kahan method, then adding in the inexactness handling, then incorporating the covariance matrices, and finally bringing it all together in this really elegant igenGK method.
It really is a testament to the power of combining different mathematical techniques and adapting them to specific challenges.
So we've got this powerful igenGK method that can generate a subspace for our solution. But how do we actually find the solution within that subspace? And how do they deal with choosing that regularization parameter, which is crucial for getting a good solution?
Those are excellent questions. The authors introduce a method called igenLSQR to solve the problem in that reduced subspace, and a hybrid approach to handle that regularization parameter.
This is where it gets really interesting.
Let's dive into those details in part 2 of our deep dive. Picking back up where we left off, we've got this really elegant igenGK method that creates a smaller, more manageable space to work in. But we still need to find the best solution within that space, and that's where igenLSQR comes in.
So it sounds like igenLSQR is the algorithm that actually crunches the numbers and spits out a solution, but it's building on all the groundwork laid by igenGK.
Exactly. Think of igenGK as creating a customized map, and igenLSQR is the navigation system that uses that map to find the optimal route. It's an iterative method, meaning it refines the solution step by step.
The paper mentions that igenLSQR is based on the idea of projecting the problem onto those Krylov subspaces we talked about earlier. Can you remind us what those are and why they're so important?
Absolutely. Remember, Krylov subspaces are those special vector spaces we generate by repeatedly applying a matrix to a starting vector. They capture the essential information about the matrix's action on that vector.
It's like seeing how a system responds to a specific input over time. Each application of the matrix gives us a new snapshot of the system's behavior.
Precisely. And by projecting our problem onto these subspaces, we're essentially focusing on the most relevant parts of the system's behavior for finding a solution.
So igenLSQR iteratively solves a sequence of smaller projected problems within these Krylov subspaces. And as we get more and more iterations, our solution gets closer and closer to the true solution in the original space.
That's the beauty of iterative methods. They allow us to chip away at the problem, gradually making progress with each step. And the authors provide a clear algorithm outlining the steps of igenLSQR.
Okay, so we've got igenK setting the stage, and igenLSQR finding the best solution within that reduced space. But we haven't talked about regularization yet. How do they choose the regularization parameter lambda, which controls that balance between fitting the data and keeping the solution smooth?
That's where their hybrid approach comes in. Instead of fixing lambda beforehand, they adjust it dynamically at each iteration of the igenLSQR process.
It's like having a smart thermostat that's constantly adjusting the temperature based on the current conditions in the room.
Exactly. They call this approach Inexact Generalized Hybrid, or igenHybR for short.
So instead of fixing lambda beforehand, they adjust it on the fly as the iterations progress.
Yeah.
What's the advantage of that?
It allows the method to adapt to the specific characteristics of the problem at each step. It's a more dynamic and robust approach, especially when we have a lot of uncertainty.
The paper mentions projecting the problem onto a lower dimensional space and then applying Tikhonov regularization within that space. Is that how this hybrid approach works?
Precisely. They use the igenT method to create this lower dimensional space, and then they carefully select that regularization parameter within that space.
This seems to be a common theme in this paper project. The problem onto a smaller space, and then do the heavy lifting there.
It's a very effective strategy for large-scale problems. It reduces the computational burden while still capturing the essential features of the problem.
I'm curious about how they actually choose that regularization parameter. The paper mentions 3 different methods: optimal discrepancy principle and weighted generalized cross-validation. Can we dive into those a bit?
Let's start with the optimal method. It's a bit of a cheat, really, because it uses the true solution to find the best regularization parameter. Of course, in real-world problems, we usually don't know the true solution, but it serves as a good benchmark.
So it tells us what the best possible outcome would be if we had perfect information. What about the discrepancy principle?
The discrepancy principle, or DP, is a more practical method. It balances the norm of the residual, the difference between the predicted and observed data, with the estimated level of noise in the data.
So it tries to find a solution that fits the data well, but also accounts for the fact that we have some inherent noise in our measurements.
Exactly, and it's a relatively easy method to implement, which is a big plus.
And last but not least, we have the weighted generalized cross-validation, or WGCV method.
WGCV is a powerful method that borrows ideas from statistical cross-validation. It tries to predict how well the solution would generalize to new data by leaving out portions of the data during the parameter selection process.
So it's a more sophisticated method that tries to prevent overfitting to the specific data we have.
Yes, and it can be very effective in certain situations, although it can also be more computationally demanding. The authors mentioned that it can sometimes struggle to find a good regularization parameter, and that weight parameter might need some tuning.
Okay, so we've got a solid grasp of the theoretical foundations of the igenGK method and that hybrid approach, but I'm always eager to see how these methods perform in practice. The paper has a whole section dedicated to numerical experiments.
Me too. Let's take a look at how they put these methods to the test. They focus on X-ray computed tomography as a real-world application.
Perfect. That's a great example of an inverse problem where we often have uncertainties in the forward model.
Yes, in X-ray CT, we're trying to reconstruct an image of the interior of an object based on projections taken from different angles. The forward model describes how X-rays pass through the object, but it's rarely perfect. We might have errors in the projection angles, variations in the X-ray source, or uncertainties in the properties of the materials we're scanning.
So it's a prime candidate for testing out these inexact methods.
Absolutely. Let's dive into their first experiment and see what they found.
Sounds good to me. They start by comparing the performance of the different methods without regularization, just to see how they behave in a more basic setting.
Right. This gives them a baseline for comparison before they add in the regularization. It's like testing out the engine of a car before taking it for a spin on the track.
They use a simulated medical phantom image and introduce random inexactness into the matrix vector products to mimic real-world uncertainties.
Interesting, they even verified the key relationships that form the backbone of the igenGK method. It seems like they are taking no shortcuts in their analysis.
Looks like those relationships hold up well, even with varying levels of inexactness. The paper also highlights the phenomenon of semi-convergence, where the solutions initially improve but then start to deteriorate after a certain number of iterations.
That's a classic issue with iterative methods. It's like climbing a mountain only to realize you've reached a false summit and the real peak is still further ahead.
The authors compare the standard GK, iGK, igenGK, and igenK methods, and it seems like the generalized methods GenK and igenGK perform better in the later iterations, even though they start off a bit slower.
That makes sense. Those generalized methods are designed to incorporate more information about the problem structure, so it's natural that they would eventually outperform the simpler methods.
But the inexact methods iGK and igenK do show slightly worse performance compared to their exact counterparts. That's not surprising given the added challenges of dealing with those errors.
True, but the key takeaway is that the inexact methods are still viable options, and their performance is not drastically worse than the exact methods. That's a big win considering they are designed to handle a much broader range of real-world scenarios.
Okay, so we've seen how the methods perform without regularization. I'm eager to see what happens when they introduce that hybrid approach and start playing with those regularization parameters. Looks like their second experiment focuses on that.
This is where things get really interesting. Now we get to see how these methods behave when we add in the intelligence of that hybrid approach. Let's dig in.
This time they use the optimal regularization parameter as a benchmark.
Right, remember, that's like having a cheat sheet to find the absolute best regularization parameter. It's not something we'd have in practice, but it gives us a target to aim for.
They compare the standard hybrid method, equi-dr, the generalized hybrid method, gen-type-br, the inexact hybrid method, i-type-br, and r-star, the inexact generalized hybrid method, i-type-br.
Quite the lineup, and the results look promising, it seems. The hybrid approaches not only lead to better image reconstructions, but also stabilize the convergence. We no longer see that pesky semi-convergence issue.
And once again, our igenHiBr method is holding its own, achieving a low reconstruction error that is comparable to its exact counterpart.
That's impressive. It shows that even with the added complexity of inexactness, the igenHiBr method can compete with methods that assume perfect knowledge of the forward model.
Okay, so we've seen that the hybrid approach with the optimal regularization parameter works beautifully, but in real life, we don't have that luxury. So how do the other regularization parameter selection methods stack up?
Excellent question. Their third experiment delves into that very topic, comparing the optimal method with the discrepancy principle, DP, and the weighted generalized cross-validation, WGCV method.
I'm on the edge of my seat. Which method reigns supreme in this practical showdown?
It seems the DP method comes out as a strong contender, achieving results very similar to those of the optimal method. This is great news because the DP method doesn't require knowledge of the true solution, which is a huge advantage in practice. It does, however, require a good estimate of the noise level.
So there's a trade-off. We gain practicality, but need to have a handle on the noise in our data. What about WGCV? How does it fare?
WGCV unfortunately doesn't perform as well in this particular experiment. The authors point out that it might need some tuning of its weight parameter to achieve better results.
That's a reminder that even sophisticated methods sometimes need a bit of tweaking to shine. But overall, it seems like the DP method emerges as a practical and effective way to select the regularization parameter for igenHiBr.
Absolutely. It strikes a good balance between accuracy and feasibility.
Okay, we've covered a lot of ground, but I have one more question that's been nagging at me in these experiments. They introduce inexactness in a rather general way. What about more specific real-world sources of inexactness, like, say, errors in the projection angles in X-ray CT?
You read my mind. Their fourth and final experiment tackles exactly that scenario. They explore how the methods perform when the inexactness stems from inaccurate projection angles.
This is where it gets really interesting. We're moving beyond the realm of theoretical simulations and into a more practical setting that directly reflects the challenges of X-ray CT.
Precisely. Let's see how they model this scenario. They start with the true projection angles and then add in some random error that decreases gradually over the iterations.
That makes sense. If you think about it, if you're doing a CT scan and you realize there's some error in the angles, you might be able to adjust the equipment and reduce that error as you go.
Right. It's like a feedback loop where each iteration informs the next one. They explore two cases, one starting with a small degree of inexactness and the other with a larger degree.
And they solve both cases with and without regularization. I'm curious to see how much of a difference that makes.
Let's first look at the results without regularization. It seems that semi-convergence rears its ugly head again, especially when the initial inexactness is large.
That highlights the importance of regularization in stabilizing the solution.
Absolutely. And when they incorporate the igenHiBr method with optimal regularization, the reconstructions improve significantly and the convergence becomes much more stable.
But here's a fascinating observation. Even though both cases end up with the same small degree of inexactness after a certain number of iterations, the one that started with a smaller error performs much better overall.
That's a crucial insight. It suggests that early intervention is key. If we can minimize errors early on, it can have a lasting positive impact on the final solution.
I'm really impressed with how this paper tackles the challenges of inexactness head-on. It's clear that the igenGK method, combined with the hybrid approach, offers a robust and practical solution for tackling large-scale Bayesian inverse problems, even in the face of real-world uncertainties.
I agree. They've laid a solid foundation for future research and applications in a wide range of fields.
This has been quite a journey through the intricate world of Bayesian inverse problems. We've gone from the basics of GK bidiagonalization to the sophisticated igenGK method and the elegant hybrid approach. We've learned about the importance of handling inexactness, the power of hybrid approaches, and the ongoing quest for better regularization techniques.
And we've been reminded that even in the face of complexity and uncertainty, there's always room for creativity, innovation, and a healthy dose of mathematical rigor.
So to our listeners, we encourage you to continue exploring this fascinating world. Don't be afraid to dive deep. Ask challenging questions and push the boundaries of what's possible. Maybe your discoveries will be the next stepping stone in this exciting field. That's all for this deep dive. Until next time, keep those brains buzzing and those curiosity fires burning.
Farewell, fellow explorers.
It's like they're handing us a flashlight and saying, go explore, see what else you can find in the dark.
Exactly. And that's what makes this paper so exciting. It's not just a solution, it's an invitation.
Okay, so let's talk about those limitations. What are some of the areas where further research is needed?
Well, one area they point out is incorporating uncertainty quantification more directly into the solution process. Right now their focus is on finding that MAP estimate.
Right, which gives us the most likely solution, but doesn't really tell us the whole story about, the range of possibilities or how confident we should be in that solution.
Precisely. They acknowledge that a more comprehensive Bayesian approach would involve estimating that full posterior distribution, which would give us a much richer understanding of the uncertainties involved.
So instead of just getting one answer, we'd get a whole probability distribution telling us, how likely different solutions are.
Exactly. And that would allow us to make more informed decisions based on the data and the model.
For example, if we're using this method to analyze medical images, knowing the full posterior distribution could help doctors make more confident diagnoses and treatment plans.
Absolutely. It would be a big step towards making these methods even more robust and reliable in those real-world applications.
What other avenues for future work did they suggest?
They also talk about exploring different regularization techniques and parameter selection methods. They acknowledge that the choice of regularization can really impact the solution, and there's always room for improvement.
They specifically call out the WGCV method, which didn't perform as well as the discrepancy principle in their experiments. They suggest that further research into tuning that weight parameter or exploring alternative cross-validation techniques might lead to better results.
It's a good reminder that even really sophisticated methods often have room for optimization and refinement. There's always that balance to strike between complexity and practicality.
And they even hint at the possibility of extending their methods to nonlinear inverse problems.
That's a natural next step. Linear problems are often a good starting point, but many real-world problems are inherently nonlinear, which adds a whole other layer of complexity. Developing efficient and robust methods for those nonlinear inverse problems with inexact forward models would be a huge breakthrough.
It sounds like they've opened up a Pandora's box of possibilities.
I agree. Their work has laid a solid foundation, and I have no doubt that future researchers will build upon their insights to develop even more powerful and versatile methods for tackling those challenges of inexactness in inverse problems.
Well, I think we've reached the end of our deep dive. We've explored that intricate world of Bayesian inverse problems, delved into that ingenious igenGK method, and seen how it can tackle real-world challenges. We've learned about the importance of handling inexactness, the power of those hybrid approaches, and the ongoing quest for better regularization techniques.
And we've been reminded that even when facing complexity and uncertainty, there's always room for creativity, innovation, and a healthy dose of mathematical rigor.
To our listeners, we encourage you to continue exploring this fascinating world. Don't be afraid to dive deep, ask challenging questions, and push those boundaries of what's possible. Maybe your discoveries will be the next stepping stone in this exciting field. That's all for this deep dive. Until next time, keep those brains buzzing and those curiosity fires burning.
Farewell, fellow explorers.
Welcome to the deep dive. Today we're going to be going deep into Bayesian inverse problems. But not just the usual stuff. We're really going to be focusing on what happens when your forward model isn't perfect.
Yeah, you hit the nail on the head. That assumption of a perfect forward model, it's a big stumbling block for a lot of the traditional methods. The paper we're diving into today really tackles that head on. It's called Inexact Generalized Golub-Kahan Methods for Large-Scale Bayesian Inverse Problems.
And this is a challenge that comes up in a lot of different areas,
Oh,
right?
absolutely. I mean, you see it everywhere, like in medical imaging when you're trying to reconstruct images from noisy data, or in geophysics where they use it to map the Earth's interior from seismic waves.
So many different places where it's relevant.
Exactly. Basically, anywhere you're trying to figure out the underlying cause from what you observe, and especially when you know that your understanding of how that cause and effect are related, it's not perfect, you're in Bayesian inverse problem land.
Okay, so let's back up a bit and talk about the basics. The paper sets the problem up with equation 1.1, which is a pretty standard linear inverse problem, x plus a equals b. But there's a catch here, right?
There is. This problem is what we call ill-posed. It means even a tiny error in your data, that little a there, can throw off your solution x by a huge amount.
Wow, so it's super sensitive.
Exactly. Think of it like trying to balance a pencil perfectly on its tip. The slightest nudge and whoops, it topples over. That's how sensitive these ill-posed problems can be.
So how do you even approach something that delicate?
Well, that's where the Bayesian approach comes in. The paper uses maximum a posteriori estimation, or MAP, which is in equation 1.3.
Okay, can you break that down for us a bit?
Sure. The MAP estimate basically tries to find the most likely solution given two things. What your data tells you, that's the B, and what you already know about the system, and that's the prior knowledge. It's like finding the best fit that satisfies both the evidence and your intuition.
So you're kind of using what you already know to help stabilize things.
Precisely. And it's really interesting because equation 1.3 actually connects back to something called Tikhonov regularization, which is a well-established way to stabilize these solutions. It adds a penalty term to prevent those wild swings that can happen with ill-posed problems.
Got it. So it's like adding a little safety net to keep things from going haywire.
Perfect analogy. Now, things get pretty interesting in section 2. When the paper does a change of variables, you see it in equation 2.2. This transformation might seem a little bit out of left field at first, but it's really crucial for making the whole thing computationally feasible.
Especially when you're dealing with these giant matrices that come up in real-world applications, right?
Absolutely.
Yeah.
Imagine trying to solve a system of equations with millions or billions of variables. It quickly becomes a computational nightmare. This change of variables helps us restructure the problem in a way that makes it much more manageable.
Okay, that makes sense. Now let's talk about something that I think is really key here, the inexactness of the forward model. The paper dives into this in section 3 and acknowledges that in most real-world situations, we don't have perfect knowledge of that A matrix.
Right, it's a big step away from those traditional methods that often assume we know A exactly. But honestly, think about it, whether it's little errors in how your instruments are calibrated or limitations in what they can measure, or just the inherent complexity of what you're studying, there's almost always some level of uncertainty in that forward model.
And so the paper captures that inexactness by introducing these error matrices, EK and FLAUK, in equation 3.5. It's not just assuming a perfect A anymore, it's basically saying, we know our model might be off, so let's build that in.
Exactly, and that's where the ingenuity starts to come in. They lay out this really clever set of iterative methods, starting with the good old Golub-Kahan bidiagonalization, which has been a workhorse for solving least squares problems for ages.
So they're building a toolkit, kind of, starting with these classic techniques.
Exactly. You start with Golub-Kahan, then you move to Inexact Golub-Kahan, or iGK, which is adapted to handle those errors in the forward model. Then you have Generalized Golub-Kahan, or igenGK, which is designed to tackle the generalized least squares problem that pops up in the Bayesian framework.
So each one builds on the last.
Exactly. And it all culminates in their big innovation, the Inexact Generalized Golub-Kahan Method, or igenGK for short, which they introduce in section 4.
And what makes this one so special?
It combines the best of both worlds. It takes the strengths of iGK and igenGK and puts them together to create this really robust method that can handle both the inexactness in the forward model and all the complexities that come with the Bayesian approach.
So it's like a more resilient solution.
Yeah.
One that recognizes that our understanding of the problem isn't perfect.
I like that, a resilient solution. Algorithm 4.1 lays out the step-by-step process, and it's really fascinating to see how it builds up the solution, refining it at each iteration, all while taking into account those pesky errors in the model.
So it's like a self-correcting process, in a way.
You could say that. Now, in section 4.2, the paper gets into the nitty-gritty of how this igenGK method is actually used to solve the least squares problem. Essentially, it projects the original problem onto a smaller subspace, making it much easier to handle.
So it's like finding a more manageable way to represent the problem.
Yeah, exactly. Equation 4.5 shows how that transformation happens. It's like finding a shortcut through a dense forest by focusing on a specific path that captures all the essential features.
I like that analogy. But even with this powerful method, you still have the challenge of choosing the right regularization parameter, lambda. And that's where the hybrid approach comes in, which the paper introduces in section 4.3.
This is a critical part. That regularization parameter controls how much weight you give to your prior knowledge versus what your data is telling you.
Like finding the right balance between what you think you know and what you're actually seeing.
Exactly. The hybrid approach estimates this parameter at each step, which makes the whole solution process much more adaptive.
Interesting. So it adjusts as it goes. And the paper gives two specific methods for finding that parameter: the discrepancy principle, or DP, and weighted generalized cross-validation, or WGCV.
And both of these methods aim to find a good regularization parameter automatically, even if you don't know the exact solution beforehand.
So it takes some of the guesswork out of the process.
Precisely. And that brings us to section 5, where the paper puts the igenGK method through its paces. What really stands out to me is the CT reconstruction example. It's like a simulation of a real-world medical imaging problem.
Can you walk us through that a bit?
Sure. They're using igenGK to reconstruct an image from X-ray projections. But here's the kicker. They're doing it even when there are errors in our understanding of how those X-rays are interacting with the object being imaged.
And it works.
The results are pretty amazing. Figures 2 and 3 show that even with significant errors in the forward model, the igenGK hybrid method can still reconstruct a pretty darn good image.
So it can see through those imperfections in our model, in a way.
It can. And there's another interesting finding that pops up in figures 5 and 6. They found that how inexact your initial model is can really affect how good your final reconstruction is going to be.
So it pays to start with the best possible model, even if it's not perfect.
Definitely. Every improvement you make in your starting point can translate into a more accurate and reliable result.
Okay, so we've been talking about how this paper deals with inexactness in the forward model. But there's another hurdle, right? That covariance matrix, Q, which represents our prior knowledge. It can be absolutely massive and a real pain to deal with directly.
Oh, that's a common headache in Bayesian inverse problems. In a lot of applications, Q can be so gigantic that you can't even store it in your computer's memory, let alone do any calculations with it.
So how do they get around that in this paper?
They get clever with it. They choose to work with something called the Matern covariance kernel, which is detailed in Appendix A.
What's so special about the Matern kernel?
It's kind of like the Goldilocks of covariance kernels. It's flexible enough to model all sorts of different patterns and relationships in your prior information, but it's also computationally efficient. You don't get bogged down in these super expensive matrix operations.
So it's a way to represent complex prior knowledge without bogging down the computation.
Exactly. And they even get into specific techniques like the fast Fourier transform, FFT, to speed things up even further when working with the Matern kernel.
Okay, now you're getting a bit too technical for me.
Basically, the FFT is like a super efficient way to do certain calculations with matrices. It's like speaking the language of matrices fluently so you can express the same ideas much faster.
I get it, a shortcut. So by putting all these mathematical insights and computational tricks together, this paper has come up with a really powerful way to solve Bayesian inverse problems, even when you're dealing with inexact models and these huge covariance matrices.
Precisely. It's a great example of how those theoretical advances can lead to really practical solutions that could have a real impact in a lot of different fields. It really is amazing to see how this paper takes on those big computational challenges. But what I find really exciting is what it means for all the potential applications out there. This goes way beyond just reconstructing CT scans.
You're right. The paper touches on a whole bunch of possibilities, but can we get a bit more specific? Where could this inexact generalized Golub-Kahan method really make a big difference?
Well, think about something like climate modeling. We're always trying to get a better understanding of how different factors impact our planet's climate, right? But those models are so complex, and there's always some uncertainty in our measurements and even in our understanding of how all the pieces fit together.
So you're saying this method could help build more reliable climate models, models that actually take those uncertainties into account.
Yeah.
That could be huge for predicting future climate change and making good policy decisions.
Exactly, and it doesn't stop there. Think about drug delivery systems. To design those effectively, you need a really deep understanding of how drugs interact with the body. But there's so much variation from person to person and even within the same person over time.
So using this method could help design personalized drug delivery systems, systems that are tailored to each patient's unique needs and how their body works. That would be a massive step forward in precision medicine.
Absolutely, and we can even take it a step further and think about applications in astronomy. Trying to create images of those distant galaxies from telescope data, that's a classic inverse problem, and there's always noise and uncertainty in those measurements.
So this method could help us get clearer and more accurate images of the universe, potentially revealing new things about the cosmos. That's mind-blowing.
It really is. And I think the key takeaway here is that this approach gives us a powerful framework for dealing with uncertainty and complexity, which, let's face it, are kind of baked into a lot of scientific and engineering challenges.
It's like we're shifting away from that idealized world where our models are perfect and embracing the fact that things are messy. We don't always have all the information, and our measurements aren't perfect.
Right, and that's a fundamental change in how we think about these problems. The paper even touches on this really interesting idea of using these inexact methods as part of a bigger optimization scheme where the forward model itself is being refined over time.
So the problem is actually learning and adapting as it goes. That opens up some pretty amazing possibilities.
Imagine a medical imaging system that not only creates images from the sensor data, but also constantly learns and improves its understanding of the underlying physics. It could completely change how we approach diagnosis and treatment.
Or a climate model that constantly integrates new data and refines its predictions. It would just keep getting better over time.
Exactly. It's all about pushing the boundaries of what's possible when it comes to solving these complex, real-world problems. It's something we can all get excited about.
This paper is truly a testament to human ingenuity and the sheer power of mathematics when it comes to helping us understand and solve those problems.
I totally agree. It's a reminder that even the most difficult problems can be tackled with the right approach. And for those of you who are eager to dive deeper into this field, the paper points us to some great resources. It mentions the IR Tools MATLAB package, which sounds like a fantastic place to start for anyone interested in exploring iterative regularization methods.
It's like a playground for anyone who wants to get their hands dirty and try out all these different approaches. Plus, the paper itself is loaded with references to other relevant research, so there's no shortage of material to explore.
This is a field that's constantly evolving, and it's incredible to see the progress being made. New methods and algorithms are popping up all the time, driven by this need to solve these increasingly complex and demanding problems.
It feels like we're just at the tip of the iceberg here. And this paper has definitely opened our eyes to the potential of these inexact methods when it comes to tackling real-world challenges. But before we wrap up, let's take a minute to recap those key takeaways from our deep dive. The Inexact Generalized Golub-Kahan method is a really powerful new tool for tackling Bayesian inverse problems when we have uncertainties in our forward model and those massive covariance matrices to contend with.
That's right. It's a robust and efficient method that pulls together insights from a bunch of different areas in mathematics and computation. And perhaps most importantly, it unlocks all sorts of possibilities for solving problems that were previously way too difficult to handle.
It's a beautiful example of how theoretical advances can lead to practical solutions that have the potential to impact our lives in countless ways.
It's a testament to the ingenuity of those mathematicians and computer scientists out there who are constantly pushing the boundaries of what's computationally feasible. This paper really showcases how those seemingly abstract mathematical ideas can have a profound impact on solving real-world problems.
And it definitely leaves us with plenty to think about. One question that talks into my mind is how this kind of approach could be applied to even more complex situations. The paper really focuses on linear inverse problems, but so many real-world problems are nonlinear.
That's a great point. Extending these methods to nonlinear problems, well, that's a hot area of research right now. There are a lot of challenges to overcome, like dealing with multiple local optimas and ensuring that the iterative process stays stable.
So it sounds like there's still a lot of uncharted territory to explore in this field.
Definitely. And that's what makes it so exciting. As we develop more sophisticated mathematical tools and our computational power continues to grow, we can tackle those increasingly complex problems that were once out of reach.
This paper really emphasizes that scientific progress is not just about finding the right answers. It's also about recognizing the limitations of our models and developing methods that can handle that uncertainty and inexactness. It's a shift from assuming we have all the answers to embracing the unknown.
It's a good reminder that our knowledge is always evolving and that there's always something new to discover. But it's also empowering because it means we can keep refining our understanding of the world and develop better solutions to the challenges that we face.
Yeah, it really is amazing to think about how these abstract mathematical concepts can actually be used to solve real-world problems.
Yeah.
And this paper, it's really just the tip of the iceberg.
Right, and I'm already thinking about what comes next. I mean, they focus on linear inverse problems here, but so many problems out there are nonlinear.
Absolutely.
Huh.
Extending these methods to those nonlinear problems, that's a huge area of research right now. It's definitely not easy. There are a lot more challenges when you go nonlinear. You have to worry about things like multiple local optima, making sure the iterative process stays stable. But if we can crack it, the potential payoff is massive.
I can imagine. It feels like there's still so much we don't know in this field, so much left to explore. Oh, for sure. It's a really exciting time to be working on this stuff. As our mathematical tools get more sophisticated and our computational power keeps growing, who knows what kinds of problems we'll be able to solve.
This paper really makes you realize that progress in science isn't just about finding the answers. It's about recognizing what we don't know. It's about being comfortable with the limits of our models.
I totally agree. This shift away from assuming we have the perfect model to embracing uncertainty and inexactness, it's a big deal.
Yeah, it's humbling in a way, because it reminds you that our knowledge is constantly changing. There's always more to learn. But it's also kind of empowering because it means we can keep getting better, keep refining our understanding and finding even better solutions.
Exactly. And on that note, I think it's time to wrap up this deep dive. We've covered a ton of ground today, from the basics of Bayesian inverse problems to the nuts and bolts of this new inexact generalized Golub-Kahan method.
It's been an awesome journey. I really hope our listeners have gained a better appreciation for the power of math, how it can be used to tackle these real-world problems that seem so complicated.
The pleasure was all mine. It's been great exploring this with you.
And to everyone listening, if you want to learn more, definitely go check out the paper and all the resources we've talked about. Keep those ears peeled for more deep dives into the world of science and tech coming soon. Until then, happy exploring. All right, let's dive into this paper. Inexact Generalized Golub-Kahan Methods for Large-Scale Bayesian Inverse Problems. It tackles these situations where our forward model isn't totally accurate.
Yeah, it's a problem you see all the time in imaging or geophysics, dealing with complex systems.
So let's start with just the problem itself. The paper jumps right into large-scale inverse problems. What makes them so hard?
Imagine trying to figure out the shape of something, but you can only see its shadow.
Oh,
That's basically what we're dealing with here. An inverse problem. You work backwards from limited data, try to reconstruct the source.
and that shadow, that's our measurements, distorted by the forward model.
Right. And often we have way more unknowns than data points. So
Yep.
there's not enough info to get just one solution. It's sensitive to noise too. Small errors can really mess things up.
So how do we even start to deal with that? The paper mentions regularization.
Regularization is like adding some constraints to narrow down the possibilities. It's like adding guidelines so the solution doesn't go completely off the rails. Okay, I get that. And the Bayesian framework is a way to do that.
Exactly. We're not starting from scratch. We usually have some idea about the solution, like from past experiments or theory. The Bayesian framework lets us include that prior knowledge.
Like a probability distribution.
Yeah, it's like saying, okay, based on what we know, these solutions are more likely.
Like having a rough sketch before you try to figure out the whole picture.
Exactly. And the Bayesian approach also lets us quantify the uncertainty in our solution.
Because we can't expect perfect answers in these messy real-world situations, right?
Right. Instead of a single solution, we get a probability distribution. tells us how likely different solutions are. And that's where maximum a posteriori estimation comes in.
MAP estimation.
It's like finding the peak of that probability distribution, the most probable solution given what we know.
Gotcha. Now let's get to the heart of the paper. Dealing with inexactness in the forward model. They call it an inexact forward problem. What does that actually mean? So imagine you're trying to reconstruct an image from X-rays. The forward model describes how the X-rays pass through the object. But what if the X-ray machine itself isn't perfect?
So it's like having a blurry lens.
Exactly. Those imperfections cause errors in our forward model. Mathematically, we can represent that with the equation A's plus A equals D.
Okay, let's break that down. D is our measurements. The slightly messed up ones. A is the forward model matrix, the relationship between the unknown and the data. And A is the noise.
Right, and the challenge is we don't always know how inaccurate A is.
So how do they tackle this? They mention a change of variables.
Remember, we're dealing with large-scale problems. A and Q, the covariance matrix, can be huge. Working with them directly is a computational nightmare, so they introduce a new variable x defined as x equals q inverse times s minus where is the mean of our prior.
So why is this helpful?
It simplifies things. First, we don't have to compute the square root of q directly. That can be really expensive computationally. Second, it makes those weighted norms from the Bayesian formulation simpler to handle.
Okay, so this sets the stage for their main contribution, the igenGK method. But before we get there, what about those other methods that they mentioned, like the Golub-Kahan bidiagonalization?
GK. That's a classic for solving least squares problems. It breaks down a big problem into smaller steps.
Manageable pieces.
Exactly. Then there's Inexact Golub-Kahan, or iGK. It acknowledges that our calculations with A aren't perfect.
Because of those errors we talked about.
Right. iGK adapts GK to handle those inexact matrix vector products.
Okay, so we've got GK, the foundation, and iGK, which handles inexactness. What's next?
Then comes Generalized Golub-Kahan, or GenK. It extends GK to work with the generalized least squares formulation. That's important for the Bayesian approach.
Because we're not just looking at the difference between the data, we're also thinking about the uncertainty in our prior knowledge.
Exactly. GenK uses the covariance matrices to weigh things properly.
So we've got these three building blocks, GK, iGK, and GenK, and now they combine them to make the new igenGK method.
Yeah. That's where it gets really interesting. They've taken the best parts of iGK and genGK to handle both inexactness and the complexity of a general covariance matrix.
And they even provide a specific algorithm 4.1.
Yep. One important feature is reorthogonalization. It helps ensure numerical stability, prevents small errors from messing up the solution.
So we've built this powerful new tool, igenGK, but how do we actually use it? That's what we'll look at next.
Okay, so we've got this powerful new tool, igenGK. But how do we actually use it to solve these inverse problems?
Well, they propose something called Inexact Generalized LSQR, or igenLSQR. It's a way to solve the least squares problem iteratively, but it builds on igenGK.
So it's like using igenK to guide us as we go.
Exactly. igenLSQR takes the problem and projects it onto the subspaces from igenK.
And that lets us solve a bunch of smaller problems instead of the whole massive thing at once.
Right. It's a divide and conquer strategy. It works really well for these large-scale problems.
Now, one thing I've always wondered about with inverse problems is regularization. It seems like finding that right balance is key. You're absolutely right. Regularization helps us control the trade-off between fitting the data and keeping the solution smooth and stable.
And the regularization is controlled by a parameter boat, right?
Yeah, exactly. Small adjusts the strength of the regularization. Small O means we focus on fitting the data, even if the solution is noisy. Large nu means we want smoothness, even if we lose some accuracy.
So how do we find the best value for low?
That's a great question. The paper suggests a hybrid approach. It combines igenK with a smart way to pick U at each step. They compare three methods: the optimal choice, which we usually don't know in real life, the discrepancy principle, or DP, and weighted generalized cross-validation, or WGCV.
Wait, so they're adjusting low as they go?
Yeah.
Based on how the solution is looking?
Exactly. It's like a feedback loop. And what's cool is that DP works surprisingly well, even though it doesn't need to know the true solution.
That's really useful for real-world applications.
Absolutely. Okay, so let's see how this all works in practice. The paper looks at X-ray computed tomography, or CT reconstruction.
CT scans are a classic example of an inverse problem, right? You're trying to make a 3D image from 2D projections.
Exactly. And they start by testing things without any regularization.
So like just throwing the ingredients together and hoping for the best.
Pretty much. And it doesn't work out great. They see something called semi-convergence. The solution starts to improve, but then it goes off track.
Why does that happen?
It's because without regularization, the noise takes over. It amplifies the errors instead of smoothing them out.
But they find that even without regularization, the generalized methods igenGK and igenGK do better eventually.
It's like they're more careful at the beginning, and that pays off later on.
Okay, so even without regularization, those methods are pretty robust.
Yeah.
But in their next experiment, they use the hybrid approach with the adaptive cover. What happens then?
The results are much better. The hybrid approach keeps things stable and leads to more accurate reconstructions.
And in experiment 3, they compare the different ways to choose, which one works best?
DP, the discrepancy principle. It does almost as well as the optimal choice, but it doesn't need to know the true solution.
Wow, that's impressive. Okay, what about experiment 4? They mentioned something about inaccurate projection angles.
Yeah, that's a common problem in CT scans. The angles of the X-ray projections might not be perfectly accurate.
So another source of error in the forward model.
Right, and they modeled this as decreasing over time, like the machine is getting calibrated as it scans.
What do they find?
The main thing is that the amount of error at the beginning is really important. If it's too big, it's hard to get a good solution, even if the error gets smaller later.
Okay, so starting off on the right foot is crucial, especially when the forward model isn't exact.
Exactly. Now, before we move on, let's talk about those Matern covariance kernels.
Those are used to represent our prior knowledge about the solution, right? Like how smooth we think it should be.
Yeah, they're really versatile. The Matern family can model lots of different smoothness levels.
And they're efficient too, computationally.
Yes, we can store them efficiently and do those matrix vector products quickly.
So to sum up this part, we've seen how IngenLSQR, combined with that hybrid approach for choosing LEDI, is really effective for solving inexact Bayesian inverse problems.
Right. And the CT reconstruction experiments show how well it works in a real-world setting.
It's all about accounting for those errors and finding the right balance with regularization. So we've covered a lot of ground. What stands out to you as the most important takeaway from this paper?
I think combining that igenGK method with that hybrid approach for choosing that, that's really a big step forward.
It gives us a way to handle those inaccuracies in the models, right?
Yeah, and it's efficient too. Plus the fact that the discrepancy principle works so well, that's huge for real-world problems.
You mentioned before that this research has implications for other areas too. What else could these methods be used for?
Oh, tons of things. Anywhere you've got noisy data and complex systems, medical imaging, geophysics, signal processing, you name it.
It's not just about making images then. It's about getting useful information from messy data.
Exactly. Like in climate modeling, there's so much uncertainty in the measurements and the models. These methods could help make better predictions.
It's like having better tools for dealing with the real world where things are never perfect.
Right. And it's not just about finding solutions. It's about knowing the limits of our models and making good decisions even with uncertainty.
That's a really important point. This research shows us that uncertainty is part of science. We don't need to be afraid of it. We can manage it.
Absolutely. By acknowledging those limitations and coming up with robust methods like these, that's how we make progress.
Well, this deep dive has been really fascinating. I feel like I've learned a lot about inverse problems.
It's been great talking about this with you.
And to all our listeners out there, keep exploring this stuff. Who knows what you might discover in the world of inverse problems? Hey everyone, welcome back. Today we're going deep, really deep, into Bayesian inverse problems.
And not just the straightforward ones. We're talking about those messy situations where things get a little fuzzy.
That's right. Specifically, we'll be diving into a paper titled Inexact Generalized Golub-Kahan Methods for Large-Scale Bayesian Inverse Problems.
Oh, yeah, that's a good one. It really highlights how mathematicians are tackling real-world problems where uncertainty is just part of the game.
Uncertainty, noise, all that fun stuff. But before we get lost in the weeds, let's set the stage. What exactly are inverse problems, and why should anyone care?
Imagine you're trying to solve a jigsaw puzzle, but some of the pieces are missing, and the picture in the box is, well, a bit faded.
Okay, I can picture that.
That's basically an inverse problem. You have some observations, the pieces you do have, and a model, that faded picture, that kind of describes how those observations relate to what you're trying to figure out.
So like trying to figure out the shape of an object based on its shadow, or like reconstructing a 3D image from a bunch of 2D X-ray projections.
Exactly, and these problems are everywhere. Medical imaging, geophysics, astronomy, you name it. The challenge is that they're often what we call ill-posed.
Ill-posed. Does that mean, like, they're badly behaved?
Kinda. It means that small errors in our observations or our model can lead to wildly different solutions.
Yikes. That sounds like a recipe for a lot of headaches. How do we even begin to tackle something like that?
That's where regularization comes in. It's all about adding constraints, like guidelines to nudge us towards solutions that make sense and aren't overly sensitive to noise.
So it's like we're adding some guardrails to keep us from going off track.
Precisely. And this paper dives deep into that, especially when the forward model itself isn't perfect.
Right, because in the real world, our picture on the box is rarely crystal clear.
Yeah.
It's like trying to solve a puzzle with a blurry picture as a guide.
Exactly. And that's where the Bayesian approach comes in. It's not just about finding a solution, but understanding the range of possibilities and how likely each one is given the data and our prior knowledge.
Okay, so it's like we're acknowledging that we don't have all the answers,
Yeah.
but we can still make informed guesses based on what we do know.
Right. The paper starts with a basic linear inverse problem, represented by equation 1.1, as plus so will D. Here, D is our observed data, those puzzle pieces.
Right, got it. And A.
A is our forward model, how the thing we're interested in generates the data we observe. S is the unknown, the complete picture, and represents that pesky noise or error.
So it's like saying the true state of things, when passed through a model, plus some inevitable noise,
Yeah.
gives us the data we see, and we're working backwards, trying to uncover that true state.
Exactly. And the Bayesian framework lets us bring in prior information, like having a hunch about what the puzzle might look like based on our past experience.
I like that. It's not just blindly sitting the data, it's bringing in some expert judgment.
Exactly. And that's reflected in equation 1.2, which introduces the posterior probability distribution function. It combines our prior beliefs with the observed data to give us an updated understanding of the possible solutions.
So it's not just finding a solution, but understanding the range of possibilities and how well each one fits the evidence.
Precisely. And a key concept here is the maximum A posteriori estimate, or MAP, represented by equation 1.3. It's finding the most likely solution based on both our data and our prior information.
Got it. It's like finding the best fit, considering both what we see and what we already believe. But here's where things get really tricky, right? What happens when our forward model, our picture on the puzzle box, is itself flawed? Like, what if it's missing pieces or the colors are faded?
That's the crux of this paper. It dives into this inexactness in the forward model. They use notations like and o to represent, approximations to the true A and A transpose.
So our picture on the box is blurry or incomplete, making it even harder to solve the puzzle.
A perfect analogy. The paper gives real examples like device calibration errors in medical imaging or uncertainty in the properties of materials in, say, geophysics. Knowing the forward model perfectly is almost impossible.
So do we just give up?
Of course not. The paper explores how to modify existing methods to account for this inherent inexactness. Traditional approaches, which often treat model errors as just more random noise, don't always cut it, especially for large-scale problems with tons of data.
So they need a more sophisticated approach.
Right. And that's where these generalized Golub-Kahan methods, or GK methods, come in. They're iterative, meaning we build up a solution piece by piece, refining it as we go.
Like starting with a rough outline of the puzzle and gradually filling in the details, constantly adjusting based on what we see and that imperfect picture we're working with.
Exactly. The paper builds on these methods, starting with the standard GK process, which generates these special sets of vectors that form what we call a solution subspace. It's like creating a framework for where we'll search for our solution.
Okay, so we're defining the boundaries of our puzzle-solving space, but we still need to find the best solution within that space.
Right. And that's where the generalized GK, or igenGK, comes in. It brings in that covariance matrix Q from our prior information. It's like giving more weight to the puzzle pieces that fit well with our initial hunch about the picture.
So if we have a strong prior belief about certain parts of the solution, the igenGK emphasizes those parts.
Exactly. The paper even shows a clever change of variables in section 2, equation 2.2, which simplifies the calculations, especially when that covariance matrix is huge.
Always good for efficiency. But we still haven't talked about that elephant in the room, that inexactness. How do these GK methods handle that?
That's where things get really interesting. They introduced the Inexact GK, or iGK, and the Inexact Generalized GK, or igenGK. The iGK modifies the standard GK process to account for that inexactness in A, making sure we're still building a meaningful solution, even with a flawed model.
It's like realizing some of our puzzle pieces are slightly warped, so we have to adjust how we fit them together.
Precisely. And then we have the star of the show, the igenK, combining the strength of both iGK and genGK, handling both that inexactness and the complexities of what we call a generalized least squares problem.
Okay, I'm following. It's like the ultimate puzzle-solving tool for when we have both imperfect information and a flawed blueprint.
Exactly. Algorithm 4.1 walks us through the igenGK process step by step, including these reorthogonalization steps. Think of it like constantly checking our puzzle assembly to make sure everything still logically fits together, even as we're working with approximations.
Sounds pretty intricate. But I can see how powerful this could be, especially when we rarely have perfect information in the real world.
And remember, it's not just building a solution space, it's about finding the best solution within that space. That's where igenLSQR enters the picture. It's like finding the most complete puzzle picture we can, given the pieces and that flawed blueprint.
Got it. So we've laid the foundation for our solution, but there's one more critical element, right? Regularization. How does that fit in?
Regularization. It's like adding those constraints to our puzzle solving, making sure we aren't misled by noisy data or imperfections in our model.
So it's like making sure our puzzle solution isn't thrown off by a few warped pieces or a faded patch on the box picture.
Precisely. And a key parameter in Tikhonov regularization is up. It controls the balance between fitting the data and keeping the solution smooth and stable.
Okay. But how do we choose the right up, especially with these complex, large-scale problems?
That's where the hybrid approach shines. It's a way to find LUPT automatically as we go, making the whole process smarter and more adaptable.
Like having a self-adjusting puzzle solver that figures out the best level of smoothing as it goes. That's impressive.
It is. The paper discusses 3 methods for selecting LUP: the optimal LUPT, the discrepancy principle, DP, and weighted generalized cross-validation, WGCV. Each has its own strengths and limitations, so choosing the right tool often depends on the specific problem.
So it's like having different puzzle-solving strategies, and some work better than others depending on the puzzle. But all this is pretty theoretical, right? Do we have any real-world examples to see how these methods perform in action?
Of course. The paper uses a concrete application: X-ray computed tomography or CT reconstruction.
Perfect example. You're reconstructing a 3D image from a series of 2D projections, very much like our puzzle analogy.
Exactly. The forward model is the process of those X-rays passing through an object and creating those projections. And they use a special type of covariance kernel, the Matern kernel, to represent the smoothness of the image we're trying to reconstruct.
So we're assuming the internal structure of the object changes gradually, not abruptly. A reasonable assumption for most things.
Right. And they put these methods to the test with numerical experiments, comparing their performance under different conditions, like varying noise levels and degrees of inexactness.
This is where it gets real. So how do they do?
Well, they found that methods without regularization, even the sophisticated igenGK, suffered from what we call semi-convergence.
Semi-convergence.
They initially seem to converge towards a solution, but then they diverge as noise takes over.
So it's like our puzzle solution starts to fall apart as we get further along, even though it looked promising at the beginning.
Exactly. The generalized methods, genLSQR and igenLSQR, perform slightly better, achieving lower errors and less noisy images. But the key takeaway: regularization is crucial, even with these advanced methods.
So it's like that glue that holds everything together.
Yes.
Yeah.
And that's why they move on to the hybrid approach in their next experiment to see if regularization could stabilize things and improve the reconstruction quality.
And they use the optimal regularization parameter, looped, right?
Right. Even though it's rarely attainable in real-world situations because you need the true solution beforehand, which we usually don't have.
It sets a benchmark, though. So what happened?
The results are in figure 3A and 3B, and they're impressive. The hybrid methods not only produce clearer images, but also stabilized convergence.
That's amazing. The hybrid approach with optimal LU seems like a game changer. But what about igenHBR, considering both inexactness and the generalized problem?
Even with that inexact forward model, igenHBR held its own. It reached a low reconstruction error, just a bit higher than its exact counterpart, genHBR.
So it's living up to that promise of robustness.
It is, but remember, this was with the optimal regularization parameter, which of course isn't realistic for most real-world scenarios. So the next big question is, how do you choose the regularization parameter when you don't know the true solution beforehand?
That's a great question, and I'm guessing that's what they explored in their next experiment.
You guessed it. They compared three methods: the optimal loop as the benchmark, the discrepancy principle, DP, and weighted generalized cross-validation, WGCV, all within that igenGK framework.
So they were putting those practical methods for choosing loop to the test. Did any of them come close to the optimal loop?
The results are in Figure 4, and, well, the discrepancy principle performed remarkably well, almost matching the optimal loop.
That's incredible. So we might have a practical way to automatically choose a good regularization parameter without knowing the true solution beforehand.
Exactly. DP relies on knowing the noise level in the data, which is often a reasonable assumption.
But what if we don't know the noise level accurately?
You're right, that's one of the limitations of DP. But when we do have a decent estimate of the noise, it's a straightforward and effective method.
So what about WGCV?
WGCV had a bit more trouble in this experiment. It seemed to have difficulty picking a good regularization parameter.
So it might be a bit more sensitive to the specific problem and the data we're working with.
Absolutely. It highlights the importance of having a variety of methods at our disposal, as different approaches might work better depending on the problem at hand.
Speaking of variety, they tackled one more challenge: inexactness in those projection angles. You mentioned it's like having a wobbly X-ray machine.
Yes, exactly. In CT reconstruction, this means the angles at which the X-rays are taken are not perfectly accurate, creating errors in the data. It's really common and can be caused by all sorts of things, like equipment calibration errors, or even the object moving slightly during the scan.
So it's like our puzzle pieces are not only warped, but also slightly misaligned. How did they simulate this? And how did igenGK handle it?
They modeled this inexactness as a function of the iteration number, simulating a scenario where the angles are refined as we go, like starting with a blurry image and gradually bringing it into focus.
Okay, that makes sense.
They tested two scenarios, one with small and one with larger initial inexactness, and Figure 5 shows what happens when they solved it without regularization.
And we see that semi-convergence behavior again, right?
Exactly. But when they applied igenGK with optimal regularization, as shown in Figure 6, the reconstructions were much better.
So catching those errors early on makes a big difference.
Absolutely. It highlights the importance of careful experimental design and robust methods.
This has been incredibly insightful. We've gone from the basics of Bayesian inverse problems to the ingenious ways these methods adapt and overcome challenges.
It really shows how mathematicians are tackling those real-world problems.
Before we move on, any thoughts on the broader implications of this work? What other fields could benefit?
Oh, the possibilities are vast. Anytime you're dealing with noisy data, imperfect models, and the need to reconstruct something you can't directly observe, these methods are valuable.
So way beyond medical imaging.
Absolutely. Think about environmental modeling, where you're trying to understand things like groundwater flow, or astrophysics, where we're inferring the properties of stars and galaxies far, far away.
It's fascinating how the same mathematical framework can apply to such different areas.
It speaks to the power of math. And the Bayesian approach lets us quantify uncertainty. We're not just getting an answer, but a range of possibilities and a measure of how confident we can be in them.
So it's not just about finding a solution, but understanding its limitations and making decisions accordingly.
Precisely. And as these methods become more efficient and accessible, I think we'll see even more creative applications.
What other hidden patterns could we discover if we embrace that inexactness?
It's a great question. Being able to find meaning in noisy data is crucial for understanding the world, and these inexact GK methods are a powerful tool for doing just that.
Well said. This has definitely given me a new perspective on how mathematicians are approaching these complex problems.
Yeah.
And I'm definitely eager to dive into those numerical experiments.
Me too. Let's break those down and see what insights we can glean.
Sounds good. We'll continue our deep dive in the next part.
Okay, so let's dig into those numerical experiments. Remember, the researchers wanted to see how these inexact generalized Golub-Kahan methods, or GK methods, would actually perform in a, more realistic setting.
Right, not just in theory. They wanted to test them with the kind of challenges we face in real-world applications.
Exactly. So in their first experiment, they used what's called a medical phantom image. It's like a test image that simulates the complexities of a real human body with different tissues and densities.
So they're essentially creating a virtual patient and then what, taking virtual X-rays?
Precisely. They simulated a parallel beam X-ray process, taking projections every 5 degrees. And to make it even more realistic, they added Gaussian white noise to the data.
So they're throwing in some simulated static to mimic real-world data, which is always messy.
Exactly. It's all about testing these methods under conditions that are as close to reality as possible. They also introduced random errors into each matrix vector product with A and A transpose.
To simulate inexactness in the forward model, right?
Yeah.
Like, what if the X-ray machine itself has some inherent inaccuracies?
Exactly. They wanted to see if these methods could still produce reliable reconstructions even when the model itself wasn't perfect. But before jumping into the reconstruction, they first made sure some key mathematical relationships held up for the igenGK decomposition.
So they were checking their math, making sure everything was solid before actually putting it to the test.
Right. Table 1 in the paper shows that the discrepancies between the expected values and the calculated ones were kind of proportional to how much inexactness they introduced.
So the more wobbly their virtual X-ray machine, the larger those discrepancies. But the key relationships still held up pretty well overall.
Yeah, for the most part. Okay, so let's get to the image reconstruction itself. They compared 4 methods: standard GK, which is also known as LSQR, inexact GK, ILSQR, generalized GK, GenLSQR, and then that inexact generalized GK, igenLSQR. And remember, in this experiment, they weren't using any additional regularization on those projected problems.
So they were really pushing these methods to their limits, seeing how they handled noise and inexactness without any extra help. What happened?
The results are shown in figure 2A and 2B, and they show a classic case of what we call semi-convergence. All the methods look promising at first, but after a certain point, the errors started to, skyrocket.
It's like building a sandcastle on a windy beach. You might make some progress initially, but eventually the wind just erodes everything faster than you can build. So even with these fancy methods, regularization is crucial.
I like that analogy. And it's true that generalized methods, GenLSQR and igenLSQR, did perform a bit better. They achieved lower relative errors and produced less noisy images compared to the standard and inexact GK methods.
So incorporating that prior information through that covariance matrix did help to some extent, even when dealing with inexactness.
It did, but the main takeaway here is that relying solely on these iterative methods without regularization leads to unstable solutions. And that's exactly why they moved on to explore that hybrid approach in their next experiment.
Right, to see if adding regularization to those projected problems could help stabilize things and improve the reconstruction quality. And I'm guessing they use the optimal regularization parameter, LOPT, as a sort of benchmark.
You got it. Even though opt is rarely attainable in practice, because it needs you to know the true solution beforehand, which we usually don't, it's still a useful baseline for comparison. So they tested the hybrid versions of all 4 methods: HiDR, GenHiBR, iHiBR, and igenHiBR.
So they added that scaffolding to their sandcastle to see if it could withstand the wind. And how did it go?
It was a big improvement. Figure 3A and 3B show that the hybrid methods not only produced much clearer images, but also, stabilized that convergence, preventing that crazy semi-convergence behavior we saw before.
Okay, so that's really promising. The hybrid approach with the optimal walk seems to be making a big difference. But I'm curious, how did igenHiBR perform specifically, considering it's dealing with both inexactness and the complexities of that generalized problem?
Even with the inexact forward model, igenHiBR did remarkably well. It achieved a low relative reconstruction error, just slightly higher than its exact counterpart, GenHiBR.
So it's living up to that promise of robustness. It can handle those messy real-world problems.
It is. But remember, this was still with the optimal regularization parameter. In reality, we usually don't know that beforehand. So the next big question is, how do we choose the regularization parameter when we don't know the true solution?
That's the million-dollar question, isn't it?
It is. So in their third experiment, they compared 3 methods: the optimal opt as the benchmark, then the discrepancy principle, DP, and finally weighted generalized cross-validation, WGCV. All of these were tested within the igenHiBR framework.
Okay, so they're putting these practical methods for choosing LUT to the test. Did any of them come close to the performance of the optimal LUP?
You'll want to check out figure 4 for the full picture, but the short answer is the discrepancy principle, or DP, did amazingly well. It practically matched the performance of the optimal LUP.
That's fantastic. It means we might have a practical way to automatically choose a good regularization parameter without needing to know the true solution beforehand.
Yeah, it's really promising. DP relies on knowing the noise level in your data, which is, often a reasonable assumption in a lot of real-world settings.
But what if we don't know the noise level accurately? What if our measurements are just inherently noisy and we don't have a good estimate of how much noise there is?
That's a good point. And you've hit on one of the limitations of DP. If your estimate of the noise level is way off, then DP's performance can suffer. But in cases where we do have a decent estimate, it's a simple and effective method.
Makes sense. So what about WGCV? How did it do?
WDCV struggled a bit in this particular experiment. It had more trouble selecting a regularization parameter that actually worked well. But, this same behavior was also observed with the GenHiBR method, suggesting it might just need some tweaking of the WGCV parameters to get better performance.
So it might be a bit more sensitive to the specific problem and the characteristics of the data.
Exactly. It shows that even sophisticated methods sometimes need a little fine-tuning to work their best for specific problems, and it also underscores the importance of having a diverse toolkit of methods.
Speaking of diverse tools, their final experiment tackled that realistic challenge of inexactness in the projection angles, that wobbly X-ray machine scenario.
Right. Remember, in CT reconstruction, this means the angles at which those X-rays are taken might not be perfectly accurate, which of course introduces errors into the data. This type of inexactness is super common in real-world settings, and it can be caused by, equipment calibration errors, the object moving a bit during the scan, or even external factors like vibrations.
So our puzzle pieces are not only warped, but also slightly misaligned. How did they simulate this, and how did igenHiBR deal with it?
They modeled the inexactness as a decreasing function of the iteration number. So it's like you're gradually refining the projection angles as you gather more information.
Like starting with a blurry image and slowly bringing it into focus as you gather more data.
Precisely. They tested two scenarios, one starting with a small degree of inexactness and another with a larger initial error. And Figure 5 shows the results for both of these when solved without regularization.
And I'm guessing we see that semi-convergence behavior again, right?
Of course. But when they applied igenHiBR with optimal regularization, which you can see in Figure 6, the reconstructions were dramatically better. The case with the smaller initial error actually achieved a much lower relative error, almost matching the performance of the exact method.
Wow, so catching those errors early on can make a big difference in the end.
For sure. It really highlights the importance of careful experimental design and those robust methods that can handle those real-world imperfections.
This has been really eye-opening. We've seen how these igenGK and igenHiBR methods give us a powerful way to tackle those large-scale Bayesian inverse problems, even when we have inexactness and noisy data.
It's a testament to the power of math and the creativity of those mathematicians who developed these tools.
Before we wrap up this part, any final thoughts on the broader implications of this work? What other fields could benefit from these methods?
Oh, tons. What's so cool about these inexact generalized Golub-Kahan methods is that they're so versatile. They can be applied to a bunch of different fields where, the challenge is to figure out what's going on based on limited and noisy data and where our models aren't perfect.
Right, like those situations where we can't directly observe the thing we're interested in. We have to kind of piece together the puzzle using indirect measurements and a model that, let's be honest, might not be entirely accurate.
Exactly. And what makes the Bayesian approach so powerful is that it lets us work with that uncertainty. We can even bring in prior knowledge to help us reconstruct things. It's not about finding that one right answer. It's about exploring all the possibilities and figuring out how likely each one is, given the evidence we have.
That makes a lot more sense to me, honestly. It's much more aligned with how we actually think and make decisions in the real world.
I agree. Think about something like environmental modeling, where you're trying to understand how groundwater flows or how pollutants might spread. Those are really complex systems, and our models are always going to be simplifications. But these methods give us a way to extract meaningful insights and make more informed predictions.
It's like acknowledging that our map isn't perfect, but it can still help us navigate the terrain, right?
Perfect analogy. And this goes beyond environmental science. Think about astrophysics, where we're trying to figure out what's going on with stars and galaxies that are incredibly far away. Or geophysics, where we're trying to image what's beneath the Earth's surface.
It seems like any field where you have these indirect measurements in complex systems could benefit from this approach.
Definitely. And I think as these methods become more efficient and easier to use, we'll see them being used in even more creative ways. Imagine using them in economics or the social sciences, where the data is often messy and the models are always evolving.
That's a really cool thought. It makes you wonder what we could discover if we really leaned into that inexactness.
It's an exciting question. Being able to extract meaning from noisy data is key to understanding the world around us. And these inexact generalized Golub-Kahan methods give us a really powerful tool for doing just that.
Well said. This deep dive has been fantastic. We've explored the challenges of inverse problems, the elegance of that Bayesian approach, and the ingenuity of these inexact GK methods. I feel like I have a much better grasp on how mathematicians are tackling some of the toughest problems out there.
It's been great exploring all this with you. I hope our listeners are feeling inspired to explore the power of inexactness in their own work.
And on that note, we'll wrap up this episode of The Deep Dive. A huge thank you to you, our expert, for making even the most complex math concepts clear and engaging. It's been a pleasure learning from you.
The pleasure was all mine. And to our listeners, keep those curious minds going. We'll catch you on the next deep dive.
Hey everyone, and welcome back to The Deep Dive. Today we'll be exploring Bayesian inverse problems. Specifically, when our forward models aren't quite perfect. We're diving into the paper, Inexact Generalized Golub-Kahan Methods for Large-Scale Bayesian Inverse Problems, which tackles solving these problems even when there are model errors.
It's such a vital area to explore, especially when we consider how often our models are really just simplifications of real-world phenomena.
Exactly. And the paper uses a great example to highlight this X-ray computed tomography, or CT. Those 3D images doctors use. It really shows how even tiny errors, like in the angles of the X-rays, can lead to big issues.
It's pretty mind-blowing when you think about it. You're basically reconstructing an image of what's inside an object just based on how X-rays pass through it. And if the angles of those X-rays are even slightly off, the reconstruction can end up being completely distorted.
Yeah, and that's where the whole challenge of inverse problems comes in, right? We're working backward from the data we observe, the X-ray readings in this case, to figure out the underlying cause, the object's internal structure.
Exactly. And the forward model is that mathematical representation of how the X-rays interact with the object. But what happens when that model isn't 100% accurate? That's where things get really interesting.
Because even the smallest error in that model can snowball into a huge problem in the final image.
Right. Precisely.
Yeah.
That's when we turn to the Bayesian framework. It's an elegant approach because it allows us to incorporate prior information, what we already know or believe about the solution. So it's like adding constraints to prevent those small errors from becoming major distortions.
So it's like saying, hey, we know human bodies don't typically have giant holes in them, and using that knowledge to guide the reconstruction process, even if the X-ray data is a little off.
Perfect analogy. The paper delves into this mathematically with equation 1.2. It shows how we combine that prior information with the data and the likelihood how well the data matches the model to arrive at the most likely solution.
And that's what's called the maximum a posteriori, or MAP, estimate.
Exactly. It's the solution that maximizes the posterior probability, given all the information we have. Now, to tackle the ill-posedness of inverse problems, where tiny changes in the data can lead to huge changes in the solution, we introduce regularization.
It's like a safeguard that prevents those small errors from completely throwing off the solution.
Precisely. And the paper demonstrates how we can represent the MAP estimate as a generalized Tikhonov problem shown in equation 1.3. Essentially, it's a balancing act. We're trying to find the best fit to the data, while also ensuring the solution stays within the realm of what's reasonable based on our prior knowledge.
So it's finding that sweet spot between fitting the data and not violating what we already understand about the problem. Now, section 2 of the paper delves into a change of variables.
Yeah.
Why is that step necessary?
It all comes down to making the problem computationally manageable. We're often dealing with large matrices like the covariance matrix Q, and working with them directly can be very computationally expensive. So the change of variables basically transforms the problem into a simpler form that's easier to solve numerically.
It's like finding a shortcut through a dense jungle. We're still reaching the same destination, but the journey is a lot smoother.
Exactly. And equation 2.2 lays out this transformation. It paves the way for using iterative methods, which are essentially algorithms that take small steps towards the solution, refining it with every iteration.
So instead of trying to solve the whole problem in one giant leap, we break it down into smaller, more manageable steps.
Precisely. And section 3 of the paper explores these iterative methods, starting with the classic Golub-Kahan bidiagonalization, or GK.
Now that sounds pretty intimidating. Can you break it down for us?
Imagine it as a way to project the original problem onto a smaller, more manageable subspace. It's like zooming in on the most important part of a picture. You're reducing the complexity while preserving the crucial information.
I like that. So it's like focusing on the most relevant piece of the puzzle.
Exactly. And equations 3.2 and 3.3 show how this is done. They construct these orthogonal bases that span something called the Krylov subspaces. Essentially, they're creating a new coordinate system that's perfectly tailored to the problem, making it easier to solve using these iterative methods.
The paper then introduces the inexact Golub-Kahan or iGK decomposition. How does that differ from the standard GK?
The iGK is designed specifically to deal with those errors in the forward model. Remember the slightly off X-ray angles we talked about? The iGK takes them into account and adjusts the solution accordingly.
So it's like a more resilient version of the GK. It can handle the imperfections we encounter in real-world models.
Exactly. Equations 3.5 and 3.6 show how error matrices EK and free K are incorporated into the calculations. It adapts to the inexactness of the forward model, leading to the inexact LSQR method, or ILSQR, which provides solutions that are less sensitive to those model errors.
Okay, I'm starting to see how these inexact methods can help us solve real-world problems where perfect models are rare. But there's another method mentioned, the generalized Golub-Kahan or igenGK. What's its strength?
The igenGK is all about handling generalized least squares problems. In these cases, the noise term isn't simply additive. Gaussian noise equation 2.2 shows this generalized form where the noise is weighted by the inverse of the covariance matrix R.
So it's like dealing with noise that's not evenly distributed?
Yeah.
Some measurements might be more reliable than others?
Exactly. And the igenGK method described by equations 3.9 and 3.9 is specifically designed to deal with these weighted noise terms. It leads to the generalized LSQR method, or GenLSQR.
Okay, so we have the GK for standard problems, iGK for inexact models, and igenGK for generalized noise. It's like we're assembling a powerful toolkit.
Exactly. And that brings us to the core of the paper, the inexact generalized Golub-Kahan method, or igenGK, described in section 4. It combines the strengths of both iGK and igenGK.
It's like taking the best tools from our toolkit and creating a super tool.
Exactly. Section 4.1 explains the igenGK decomposition, and equations 4.1 and 4.2 illustrate how it merges the error handling capabilities of iGK with the generalized noise handling of igenGK. Both the error matrices and the weighted noise term are incorporated.
So we've created a method that's both robust and adaptable. It can handle model errors and complex noise structures all in one.
Precisely. And algorithm 4.1 lays out the steps for implementing this method. It ensures that the solution subspaces remain orthogonal, even with all the inexactness and complexity. It's a remarkable achievement.
Now we have the decomposition, but how do we actually use it to solve the inverse problem? That's where the inexact generalized LSQR method, or igenLSQR, comes into play, right?
Absolutely. Section 4.2 describes how igenLSQR leverages the igenGK decomposition to find the optimal solution to the generalized least squares problem. You can see this process laid out in equation 4.3.
So it's like we're using our super tool to navigate this intricate path towards the best solution.
Exactly. And once we've found the solution in this projected subspace, we can then translate it back to the original problem using equation 4.6. It's like after exploring a simplified version of the terrain, we're now converting our map back to the original coordinates.
This igenGK approach is so elegant and powerful, but we haven't discussed regularization yet. That's a crucial element in solving inverse problems, isn't it?
You're absolutely right. Regularization helps stabilize the solution and prevents it from being overly sensitive to noise. And the paper addresses this head-on. Section 4.3 introduces the inexact generalized hybrid approach, which specifically tackles the challenge of finding the right amount of regularization to apply.
And that's the key point, isn't it? How do we determine the optimal level of regularization? Too much, and we risk over-smoothing the solution and losing important details. Too little, and we might be overwhelmed by noise.
Exactly. That's the million-dollar question. The paper explores 3 methods for selecting the regularization parameter, lambda, the optimal method, the discrepancy principle, DP, and the weighted generalized cross-validation, WGCV method.
Okay, let's break those down. The optimal method sounds ideal, but I suspect it's not always practical in real-world scenarios.
Yeah, you're right. The optimal method requires knowing the true solution beforehand, which is rarely the case. It's like having a blueprint for the perfect Lego castle, but in real life, we often have to build without a complete set of instructions.
So that's where the DP method steps in. Can you remind me how it works?
The DP method is based on the idea that our model's predictions shouldn't try to fit the noise in the data perfectly. It aims to find the lambda value that balances fitting the data while accounting for the inherent uncertainty.
It's like accepting that our map is a bit blurry and not getting hung up on every little detail. Instead, we focus on the general direction.
Precisely. Equation 4.8 demonstrates how the DP method works. It minimizes the discrepancy between the difference between our prediction and the actual data and the estimated noise level.
So the DP method seems like a good option when we have a reliable estimate of the noise level. But what about situations where that's not the case? Isn't that where the WGCV method comes in?
Exactly. The WGCV method is particularly valuable when we don't have a clear understanding of the noise level. It uses a clever technique called cross-validation to estimate how well the solution would generalize if we left out certain data points.
It's like testing the sturdiness of our Lego castle by giving it a gentle shake. We're checking its stability without having to take it apart.
That's a fantastic analogy. Equation 4.9 lays out the formula for the WGCV method. While it might seem a bit complicated at first glance, the key is that it gives us a way to choose lambda without relying on prior knowledge of the noise level.
Okay, so we have an array of regularization methods at our disposal. It's incredible how the igenGK approach provides this adaptable framework that can handle both inexactness and regularization. But I'm really curious to see how all of this theory plays out in practical applications. The paper presents some intriguing numerical experiments in section 5, right?
Absolutely. They put these methods to the test using the X-ray CT scenario we've been discussing. In section 5.1, they begin by comparing the GK, igenGK, GenG, and igenGK methods without any regularization. It's like seeing how far we can get with the fundamental building blocks. No support structures allowed.
So it's a baseline test to assess how these methods perform on their own, dealing with the inherent challenges of inverse problems.
Exactly. They use a medical phantom image, which is a simulated cross-section of a body, and add noise to the data to mimic the imperfections of a real CT scanner.
I can imagine the reconstructed images being quite noisy without the stabilizing effect of regularization. What do the results look like?
The reconstructions are shown in Figure 2a, and as you anticipated, they do exhibit significant noise. You can discern the general shape of the phantom, but the finer details are obscured.
It's like peering through a fogged-up window. You can vaguely make out what's there, but the image lacks sharpness.
An excellent description. Figure 2b then shows the relative error norms, which quantify how far each solution deviates from the true phantom image. And all the methods display a phenomenon called semi-convergence. They start off converging toward the true solution, but then the noise takes over and the errors begin to increase.
It's like they're on the right track initially, but then get thrown off course by the interference of noise.
Precisely. And this really emphasizes the critical role of regularization. Even the most sophisticated methods can be led astray by noisy data without it.
So regularization is like our compass. It helps us stay on course and reach a more accurate destination.
Precisely. Now in section 5.2, they repeat the reconstructions, but this time they introduce the hybrid approaches with optimal regularization. It's like they're adding those much-needed support structures to stabilize the solutions.
So this is like the premium version of the experiment, where they're using the ideal amount of regularization to see just how much improvement they can achieve.
Yeah.
What do the results reveal?
The results shown in Figure 3a are truly remarkable. The reconstructed images are significantly clearer and sharper compared to the previous set. The noise has been substantially reduced.
It's like the fog is cleared, and we can now see the details of the phantom with much greater clarity.
Exactly. Figure 3b confirms this improvement. The relative error norms are significantly lower and much more stable. This clearly demonstrates the effectiveness of regularization in achieving more accurate solutions.
Okay, so the hybrid approaches coupled with optimal regularization are performing exceptionally well. But it's important to remember that this is somewhat of an idealized scenario. In real-world applications, we typically don't have a luxury of knowing the optimal regularization parameter beforehand.
You're right. So in section 5.3, they investigate how the DP and WGCV methods perform when we have to estimate the regularization parameter. They compare the igenHiBR method using the optimal DP and WGCV approaches for choosing lambda.
I'm eager to see how these methods stack up against each other in a more realistic setting. Which one comes out on top?
The results displayed in Figure 4 offer some fascinating insights. The DP method actually performs incredibly well, achieving relative error norms that are very close to those obtained with the optimal method.
That's impressive. So even without prior knowledge of the true solution, the DP method manages to identify a near-optimal regularization parameter.
It does. But it's crucial to remember that the DP method relies on a good estimate of the noise level in the data. If our noise estimate is inaccurate, the DP method might not be as effective.
It's like navigating with a blurry map again. If our understanding of the terrain is flawed, we're bound to make mistakes. What about the WGCV method? How does it fare in comparison?
In this particular example, the WGCV method encounters more challenges. Its relative error norms are higher and less stable compared to both the DP and optimal methods.
So for this specific problem, it seems like the DP method might be the more dependable choice, provided we have a reliable estimate of the noise level.
That's a sound conclusion. However, it's essential to emphasize that the ideal regularization method is highly dependent on the specific problem we're tackling and the characteristics of the data. There isn't a one-size-fits-all solution.
Okay. It's all about selecting the right tool for the task at hand and understanding the strengths and weaknesses of each method. Now let's shift our focus to section 5.4, where they address a particularly intriguing scenario: inexactness arising from errors in the projection angles of the CT scanner. Why is this aspect so important to consider in real-world applications?
Because achieving perfectly precise angles in CT scanning is incredibly difficult in practice. Mechanical limitations, patient movement, even slight vibrations in the environment can all introduce errors into those projection angles.
It's like trying to take a perfectly still photograph of a moving object.
Yeah.
There's always a chance of blur or distortion. And as we've discussed, even minor errors in those angles can have a cascading effect, leading to significant artifacts in the reconstructed image.
Exactly, and that's precisely what they aim to simulate in this experiment. They introduce random errors into the projection angles and then gradually decrease the magnitude of those errors over successive iterations.
So you're mimicking a scenario where the scanner is becoming progressively more accurate, perhaps due to ongoing calibrations or a more stable scanning environment.
Precisely. They then test the igenGK method both with and without regularization, showcasing the results in figures 5 and 6. I'm curious to hear your observations on how those angle errors influence the reconstructions.
Looking at figure 5, which shows the reconstructions without regularization, it's clear that the images are quite noisy and distorted, particularly when those initial errors in the angles are large. It's like those early inaccuracies cast a long shadow over the entire reconstruction process.
A very insightful observation. Even if those errors diminish over time, their initial impact can linger, affecting the overall clarity of the reconstruction. It underscores the importance of striving for accuracy right from the start.
Now, when we compare those results to figure 6, where regularization is applied using the igenGK method, the difference is remarkable. The reconstructions are substantially clearer, and the impact of those angle errors is visibly reduced. It's like regularization acts as a stabilizing force, guiding the reconstruction process toward a more accurate representation despite those initial imperfections.
Precisely. Regularization helps mitigate the distortions arising from those early errors, steering the solution toward a more faithful representation. Did you notice that they test two distinct scenarios? One with small initial angle errors and one with larger ones.
Yes, I did. And the results clearly demonstrate that the magnitude of those initial errors does have a significant impact. Even though both scenarios eventually converge to very small angle errors after numerous iterations, the reconstructions obtained from the scenario with smaller initial errors are noticeably better.
That's a key takeaway. It highlights that the path we take to reach the solution matters just as much as the final destination. Starting with larger errors, even if we eventually manage to minimize them, can have a lasting effect on the quality of the reconstruction.
It's a powerful reminder that in any problem-solving process, paying attention to those initial conditions and striving for accuracy from the very beginning can significantly influence the outcome. And in the context of CT scanning, this emphasizes the importance of meticulous calibration procedures and ensuring a stable scanning environment to minimize those initial angle errors as much as possible.
Absolutely. The more accurate we are from the outset, the better the reconstructions will be.
Okay, those numerical experiments have been incredibly insightful. They provided a tangible demonstration of both the challenges posed by inexactness in inverse problems and the power of the igenGK method and regularization techniques to address them. Could you briefly summarize the key takeaways from those experiments before we move on?
Certainly. We've seen clear evidence that inexactness in the forward model, whether due to inherent model limitations or errors in the measurements we take, can significantly impact the solutions we obtain when tackling inverse problems.
It reinforces the old adage, garbage in, garbage out. If our model or the data we feed into it are flawed, the results will inevitably reflect those flaws.
Precisely. But on a more positive note, we've also witnessed the remarkable ability of the Bayesian framework and regularization techniques to mitigate these challenges. By thoughtfully incorporating prior information and carefully selecting the appropriate regularization parameter, we can arrive at more accurate and robust solutions, even when faced with inexactness.
It highlights that it's not simply about having the most advanced algorithms at our disposal. It's about understanding the problem, the data, and the tools we're using, and applying them strategically and with careful consideration.
Well said. It's about choosing the right tool for the job and understanding its strengths and limitations. Now, I'm particularly intrigued by the potential applications of these methods beyond the realm of medical imaging. We've hinted at broader implications, but I'd love to explore those further.
That's an excellent point. Let's shift gears and delve into some of the diverse domains where inexact inverse problems arise and see how these techniques offer promising solutions.
So we were discussing how in real-world scenarios, we often don't know the optimal regularization parameter beforehand.
Right, and that's where those other methods, the DP and WGCV, come in to help us estimate it.
Exactly. And in section 5.3, the researchers dive into how well those methods perform. Specifically, they compare the igenGK method using the optimal DP and WGCV approaches for determining lambda.
Okay, so they're putting those methods to the test in a more realistic setting where we have to rely on estimations. What do the results shown in Figure 4 tell us?
The findings are pretty interesting. The DP method shows remarkable resilience, actually achieving relative error norms that are surprisingly close to those we get with the optimal method.
Wow, so even without knowing the true solution, the DP method can pinpoint a near-optimal regularization parameter.
It can, but it's important to note that the DP method relies on a good estimate of the noise level in the data. If our noise estimate is off, the results might not be as reliable.
It's like trying to follow a blurry map. If we don't have an accurate understanding of the landscape, we're more likely to get lost. What about the WGCV method? How does it compare?
In this particular example, the WGCV method faces a bit more difficulty. The relative error norms it produces are higher and less stable than those achieved by both the DP and optimal methods.
So it seems like for this specific problem, the DP method might be the more trustworthy choice, as long as we have a good grasp of the noise level.
That's a reasonable conclusion. But it's important to emphasize that the ideal regularization method really depends on the specific problem and the characteristics of the data. There isn't a one-size-fits-all solution.
Right, it's about choosing the right tool for the task and understanding its strengths and limitations. Now let's move on to section 5.4, where the paper tackles this really interesting scenario, inexactness, stemming from errors in the projection angles of the CT scanner. Why is this so crucial to consider in real-world situations?
Because achieving perfectly precise angles in CT scanning is incredibly difficult. Mechanical limitations, tiny patient movements, even slight vibrations in the room can all introduce errors into those projection angles.
It's like trying to take a perfectly still picture of something that's moving. There's always a chance of some blur or distortion. And as we've discussed, even small errors in those angles can have a cascading effect, leading to significant artifacts in the reconstructed image.
Precisely. And that's exactly what they aim to simulate in this experiment. They introduce random errors into the projection angles and then gradually decrease the magnitude of those errors over successive iterations.
So they're simulating a scenario where the scanner is becoming progressively more accurate, maybe through ongoing calibrations or in a more stable scanning environment.
Exactly. And then they test the igenGK method both with and without regularization, presenting the results in figures 5 and 6. I'm curious to see your observations on how those angle errors affect the reconstructions.
Well, looking at figure 5, which shows the reconstructions without regularization, it's pretty clear that the images are quite noisy and distorted, especially when those initial errors in the angles are large. It's like those early inaccuracies set the stage for a less clear reconstruction overall.
That's a great observation. Even if those errors eventually become smaller, their initial impact can linger, affecting the overall quality of the reconstruction. It really underscores the importance of striving for accuracy right from the start.
Now, when we compare those results to figure 6, where regularization is applied using the igenGK method, the difference is striking. The reconstructions are much clearer, and the effect of those angle errors is noticeably diminished. It's like regularization acts as this stabilizing force guiding the reconstruction towards a more accurate representation, even with those initial imperfections.
Exactly. Regularization helps to counteract those distortions from the early errors, nudging the solution toward a more accurate outcome. Did you notice that they test two different scenarios? One with small initial angle errors and one with larger ones?
Yes, I did. And the results really highlight how the magnitude of those initial errors does make a difference. Even though both scenarios eventually end up with very small angle errors after many iterations, the reconstructions from the scenario that started with smaller errors are visibly better.
That's a crucial point. It shows that the path we take to get to the solution matters just as much as the end result. Starting with larger errors, even if we eventually manage to correct them, can still affect the quality of the reconstruction.
It's a good reminder that in any problem-solving process, those initial conditions matter. Driving for accuracy from the start can significantly impact the final result. And when we think about CT scanning, it emphasizes how important careful calibration and a stable scanning environment are to minimizing those initial angle errors as much as possible.
Absolutely. The more accurate we can be from the outset, the better the reconstructions will be.
Those numerical experiments were really eye-opening. They really showcase the challenges we face with inexactness in inverse problems, but also the power of the igenGK method and regularization techniques to overcome those challenges. Before we move on, can you briefly summarize the key takeaways from those experiments?
Of course. We've seen concrete evidence that inexactness in the forward model, whether it's due to limitations in the model itself or errors in our measurements, can really impact the solutions we get when dealing with inverse problems.
It's like that saying, garbage in, garbage out. If our model or data are flawed, the results will inevitably reflect those flaws.
Exactly. But on a more encouraging note, we've also seen firsthand how powerful the Bayesian framework and regularization techniques can be in tackling these challenges. By incorporating prior information and carefully choosing the regularization parameter, we can get more accurate and robust solutions even when facing inexactness.
It highlights that it's not just about having the most sophisticated algorithms. It's about understanding the problem, the data, and the tools we're using, and knowing how to apply them effectively.
That's a great way to put it. Now, I'm particularly fascinated by the potential applications of these methods beyond the world of medical imaging. We've touched on some broader implications, but I'd love to dive deeper into those.
That's a great segue. Let's shift our focus and explore some of the other areas where inexact inverse problems come into play and how these techniques can offer solutions. Okay, so we've really dug into inexact inverse problems and explored the igenGK method and regularization techniques. We've even seen how effective they can be in handling those errors in CT scan reconstructions. But medical imaging is just one application. I'm curious about other areas where these challenges pop up.
Oh, absolutely. Medical imaging is just one example. Inexact inverse problems are everywhere, especially in fields that deal with complex systems and data that's inherently noisy.
Okay, so give me some examples. Where else do these techniques prove useful?
Well, think about something like hurricane prediction. Weather forecasting relies on these complex atmospheric models, but they're always simplifications of a system that's incredibly chaotic and always changing.
Right, there's so many factors at play. It's like trying to predict which way a leaf will blow in a hurricane. It's almost impossible to account for everything perfectly.
Exactly, and that's where these inexact inverse problem techniques come in. They provide a framework for incorporating our knowledge, the data we gather, and the inherent uncertainties to make more informed predictions, even when our models aren't perfect.
So by acknowledging that our models have limits and embracing that uncertainty, we can actually make better predictions.
Precisely. It's about being realistic. Instead of aiming for unrealistic precision, we recognize the inherent limitations and use these techniques to extract meaningful information and make more informed decisions.
That's pretty incredible. What other areas can benefit from this approach?
Let's switch gears to financial markets. For example, analysts use these intricate models to understand economic trends, assess risks, and make investment choices. But these models, no matter how sophisticated, are still simplifications of a highly complex and interconnected system.
Right. The market is constantly being influenced by news events, global happenings, investor sentiment. It's like trying to sail across a rough sea with a map that keeps changing with the waves.
Exactly. Unexpected events can throw off even the most carefully developed models. And in this volatile environment, inexact inverse problem techniques give us the tools to deal with that uncertainty and make smarter decisions.
So by accepting that our financial models has limitations and acknowledging the unpredictable nature of the market, we can create more robust investment strategies.
Absolutely. It's all about incorporating risk, acknowledging the unknowns, and continuously adapting to new information as it comes in.
Okay, I'm starting to see how these techniques extend far beyond just enhancing image reconstruction. Do any other examples come to mind?
Let's dive into geophysics for a moment. Scientists use seismic waves to explore the Earth's interior. They analyze how these waves travel through different layers and structures. But interpreting those seismic signals, that's a classic inverse problem.
Right, we're trying to understand the structure of something we can't directly see based on indirect measurements.
Exactly. And our models of the Earth's interior, although very detailed, are still approximations.
Hmm.
We have to account for variations in things like rock composition, temperature, pressure. All these factors affect how seismic waves travel.
It's like trying to decode a message that's been distorted as it traveled through a complex network.
Perfect analogy. And that's where these inexact inverse problem methods are so valuable. They help us extract useful information from these noisy, incomplete seismic signals, ultimately improving our understanding of the Earth's structure and composition.
Wow, this is really fascinating. I'm starting to see inexact inverse problems everywhere. It seems like any field that deals with complex systems and indirect measurements could benefit from these techniques.
You're absolutely right. From understanding climate change to designing new materials, from optimizing traffic flow to analyzing social networks, these methods give us a powerful way to navigate complexity and extract knowledge from imperfect data.
This has been an incredible exploration. We've covered so much ground from the theoretical foundations to the practical challenges and the vast potential of inexact inverse problems. I feel like I have a whole new appreciation for how mathematics can help us understand the hidden workings of the world.
That's wonderful to hear. It really speaks to the ingenuity of mathematicians and their dedication to understanding, even in the face of uncertainty.
As we wrap up this deep dive, what's the one key takeaway you hope our listeners will walk away with?
I hope they'll remember that even when we're dealing with inexactness, even when our models aren't perfect and our data is messy, there's always a path to clarity and insight. By embracing the Bayesian framework, using regularization techniques, and choosing the right mathematical tools, we can navigate complexity, uncover hidden truths, and make better decisions in a world that's full of uncertainties.
That's a great point. It's a reminder that accepting uncertainty doesn't mean abandoning precision. It means recognizing our limitations, being adaptable in our approaches, and leveraging the power of math to understand the world around us.
It's also a reminder that mathematics isn't just about abstract formulas and theorems. It's a living language that helps us describe the universe and our place in it.
On that inspiring note, we've come to the end of our deep dive. Thanks for joining us on this incredible journey.
It's been a pleasure sharing these insights with you.
You've been listening to The Deep Dive. We'll be back next week with another fascinating topic. Until then, stay curious.